So first of all, I would like to be in the spirit of the week, to start with a slogan. So I should say that all my lectures will be devoted to explain the slogan. So the slogan is that rational points on rational curves have similar behavior. So I should say at once that, like in politics, this slogan is not completely true. But as presidential candidates, I hope to be able to convince you before the end of the week that there is some truth in it. So I should say also that, in fact, in what I'm going to explain, there are still many open problems. So I hope to be able to give some of them during the talks. And finally, I should also stress that it's not necessary to go to very complicated examples to have already some nice pathologies. So I will use quite simple examples just to show you what kind of troubles there is and how you can make the things work. So in fact today will be devoted to the most simple examples, namely Pn, the projective space. So of course it's not a pathology. I mean, for this particular case you can compute everything, you can show that everything is as expected, but it's a good example to start with. So if you have already heard about it, I'm sorry, but I will spend the first talk about the projective space. Okay, so maybe I should start by introducing the main actors in display. So in fact, there are three of them. The one I'm most interested with is the field of rational numbers, Q, and the field of function of P1 over any field little k. But in fact there is some guy in between, which is Fp of t. And these three actors form a classical triangle, love triangle. So, and in fact, as in many love triangles, the relationship are more intimate along two of the edges. So there are very strong relationship between Q and Fp of t, and Fp of t and K of t. And what I want to do is in fact how you can go from Q to K of t. Although I should say also that Fp of t in fact has a double identity. So on this side it's called a global field. On the other side it's called a function field. And in fact each side corresponds to language, so I have to also to explain some kind of dictionary between the two languages. So the two languages I'm speaking of are on this side arithmetics, and on the other side it's more the language of geometry. Okay, so as the first example in this dictionary, there is the way to measure the size of solutions of equations, and to start with the size of points in the projective space. So on this side, so it should be A1. The classical terminology is the terminology of height. So let me give the simplest example of height. So it will be, well, a function which goes from Pn of q to the field of real numbers. And its definition is given by, well, h of points with homogeneous coordinates x0, xn is equal to the maximum of the usual absolute value of the xi if x0, xn are coprime integers. Okay, so this defines a function which is called height. And which measures the size of a point in the projective space. So on the geometry side, the traditional terminology is degree. So I'm sorry, I'm switching back and forth between the blackboards, which is not so good for the cameras. Anyway, so on the other side, I have the notion of degree, which can be defined in a very similar way, namely, if I go from the projective space over k of t to R, and is defined by the degree of P0 Pn is equal to the maximum of the degrees of the Pi if P0, Pn are coprime polynomials. So, as you may see quite easily, this is to have a strict analogy between both sides. You have to consider rather the logarithmic height by taking the logarithm of height, of the height, so this is called logarithmic height. And this corresponds really to the degree. Okay, so now we have defined the size of a point in the projective space. What are we interested in? Then, well, we take some subsets of the projective space, and then we look at the set of the point in that subset with a bounded height or degree. So on this side, well, let's denote it by M, B, well, no, well, I need some notation, well, it doesn't matter, Pn H of B, which will be the set of points in the projective space. Later on, I will look at points in projective variety, such that the height of the point is less than b. So this is some subset of the projective space, which is finite. And I consider it for b a real number, and later on I will make b goes to infinity and try to understand this set as b goes to infinity. Well, so I should show you, if you have never seen that, a picture of this set. So this is the projective plane, P2 of Q, and I think the upper bound I used for the points is something like, well, I don't remember if it's 100 or 1000, something like that. Anyway, I choose the bound so that the picture is nice. And the point in the middle is the point with coordinates 0, 0, 1. And the points in the upper left, well, no, I should say upper right corner is the point with coordinates 1, 1, 1. Okay, so when you look at this picture, you realize that, well, okay, so many lines are appearing. In fact, the clearest lines are the one with equation with small coefficients, small integral coefficients. But nevertheless, somehow the points are quite well distributed on the whole of the projective plane. So I will come later on that and try to explain the distribution of the points on the projective space or other varieties. So as we have seen in Carolina's talk, on the side of geometry, we are interested in a moduli space. So on this side, we want to understand the geometry of, well, we have seen that there is a scheme defined over K, which I shall denote by the scheme of morphism from P1 over K to Pn. And I take the morphism of degree D. So, as we have seen, well, in particular, there is a bijection between the set of points of this scheme which are defined over little k and the morphisms, well, I should say the set of morphism from P1 to Pn over little k, such that the degree of f is equal to d. So here I should stress something which is important. Well, if you take a point, well, there is a bijection between the points of the projective space over the field K of t to the morphism from P1 to Pn, well, which is given by, if I take a morphism from P1 to Pn phi, then I can look at the image of the generic point. And conversely, if I take a point in the projective space defined over K of t, well, then this means that I have a morphism from an open subset U of P1 to Pn. But of course, this Pn is complete. We may extend it into a morphism from P1 to Pn. So this is a bijection. So that's the reason for which, instead of studying Pn of K of t, we can as well consider the morphism. Okay, so up to now, I only explain what we are about to do. So, let me explain what we can compute for the projective space over Q and over K of t. So I start with computing things for Q. So the result. So I will look at the cardinal of the set. So I should write n, p, n, h of B to be the cardinal of the set I define over there, m, p, n, h of B. And the result is that, well, this cardinal is equivalent, as B goes to infinity, to 2 at the power n divided by zeta of n plus 1, where zeta q is a usual Riemann function, times b at the power n plus 1. And well, this is something you can already find in the book by Adi and Wright in 1938, at least for n is equal to 2. And then it was, well, in fact, looking at number of points of bounded height on projective varieties came a little bit later on and was not looked at that time, but in fact the result is already there. Anyway, so the proof goes as follows. Well, by definition, well, the number of points on bounded height on the projective space, this is half of the cardinal of the set of x naught xn in z at the power n plus 1, such that, first of all, the GCD of the xi's is equal to 1, and the maximum of the absolute values of the xi's is less than b. So there is a factor 1/2 because, of course, we can lift a point in the projective space to 2 points which satisfy this condition, GCD is equal to 1. They are opposite to each other. Okay. Well, the trouble in that set is coming from the GCD of the xi is equal to 1. Because, of course, if I look simply at the x naught xn in z at plus 1, so the maximum of the coordinates is less than b, it's very easy to estimate that. So I want to remove the GCD condition from this, and for this I use the Möbius function, the usual Möbius function. So let me remind you that this is a map mu which goes from the strictly positive integers into -1, 0, and 1, and which is given by the following conditions. So first of all, one has that mu AB is equal to mu A of A times mu of B if the GCD of AB is equal to 1. And for powers of prime numbers, so mu of P of K is equal to 1 if K is equal to 0, -1 if K is equal to 1, and 0 otherwise. Otherwise. Where P is a prime number. Well, this function satisfies the following relation. So one has that if one looks at the indicatrix function, so of the set 1, so this is equal to 1 if x belongs to I and 0 if x doesn't. So anyway, the indicatrix function for 1 is equal to the sum for d strictly positive of mu of d, the indicatrix function of d z. So this implies that the cardinal I'm interested in, so n p n h of b, is equal to 1/2 of the sum for d strictly positive of mu of d times the cardinal of the x naught xn in dz at the power n plus 1 different from 0, such that well, the maximum of the coordinates is less than b. So I should stress that here I have to remove 0 just to be sure that this sum is in fact finite. So I have only a finite number of terms which are different from 0. Okay, so now I'm almost finished, because this I can evaluate very easily. Namely, I know that, well, the cardinal of this set, so in dz at the power n plus 1 minus 0, such that the maximum of the coordinates is less than b, well, this is exactly the same as the cardinal of the x naught xn in z power n plus 1 minus 0, such that the maximum of the coordinates is less than b over d. And this is equal to 2 times the integral part of b over d plus 1 at the power n plus 1 minus 1, because I remove 0. So finally, I get a precise formula for this number, which is, well, 1/2 of the sum for d strictly positive of mu of d of this thing. So 2b over d plus 1 over n plus 1 minus 1. Okay, and you note that this is 0 if d is bigger than b. Okay, so now, well, noting that, we realize that there is some constant c strictly positive, such that for any b on d, we have that 2b over d plus 1 at the power n plus 1 minus 1 minus, well, 2 at the power n plus 1 b at the power n plus 1 over d at the power n plus 1 is less than c b over d at the power n. So in fact I could write it with a b prime, maybe it would have been clearer. Anyway. Using this inequality, I get that the absolute value of n p n h of b minus the sum for d strictly positive of mu of d b at the power n plus 1 divided by d at the power n plus 1, this is less than the sum for 1 less than d less than b of c b over d at the power n plus, well, for d bigger than b, the only thing which remains is coming from this factor. So for the sum for d strictly bigger than b, mu of d I can forget about it because it's less than 1 in absolute value, so b at the power n plus 1 over d power n plus 1. And finally, this is less than 1. So here I have to take into account that if n is equal to 1, here I get something which is in log of b, 1 over d, give a term which is like a logarithm of b, so this is less than b logarithm of b, I forgot the constant c, if n is equal to 1, and otherwise it's less than constant c prime times b at the power n if n is strictly bigger than 1. So it finishes the proof, because in both cases the exponent is less than n plus 1. And we have proven the result, and we have even a quite good estimate of the error term. Okay, so that's the thing we get over Q. So now let's do the same in the geometrical setting. So it will be B2. So you may have noticed that in the previous lectures, the 1A, B, 1, and so on were quite linear. We started with A and then we were doing B. But here it's two-dimensional, so A and B is in one direction and the numbers in the other. Anyway, so B2. So Pn over K of t. So we have already seen in Caroline Stoke how to do that. So let me simply make the result a little bit more precise. So the result may be written as follows. Okay, so there is a sequence of subvarieties of p power n plus 1 d plus 1 minus 1. Let me write it on the next line. P n plus 1 minus 1, which I denote by, let's say, fd dn contains f d minus 1 dn up to f minus 1 dn, which is the empty set. So that, well, first of all, fd dn is Pn plus 1 is an open subset of this projective space, which is obtained by removing a subspace of dimension, well, I think it's n plus 1 d minus 1. And also, if I look at f of I dn, well, minus f I minus 1 dn, then this is isomorphic to the morphism of degree I from P1 over little k from P1 of k to Pn of k times A over k at the power d minus I. Okay, so let me check this formula by proving it. So the proof was already outlined in previous lectures, so nothing new here. So as you shall see, it's very similar to the last proof I gave. Namely, if I look, well, if I look at the set I'm interested in, so the morphism, in fact, of degree d going from P1 over little k to Pn, then if I look at the points over k, this is simply given by the set of, by definition again, k of, well, the projective space, such that, well, the GCD of P naught Pn is equal to 1, and the maximum of the degrees is equal to D. Well, I should have said that the PI belongs to K of T, of course. Otherwise, it doesn't make sense. So now I have to understand this set. Well, in order to do this, well, let me introduce some notation. So I denote by, well, K of T with index D to be the set of polynomials in K of T with the degree of P less or equal to D. And inside that, I take the polynomials of degree D with the dominant coefficient equal to 1. So let's denote it by I of D. So this is the polynomials of form T power D plus A1 T D minus 1 plus N. And of course, this is isomorphic to the affine space of dimension D on K. Okay, then if we look at that, again, there is something which is very easy to understand, is the condition about the maximum of the degree to be equal to D. So the only thing which remains to understand is a GCD condition, exactly as in the number field case. And again, it's quite easy. If the GCD is not equal to 1, it is equal to some polynomial, and we may divide all the polynomials by this GCD. So more precisely, I have a map well, how to write it? I have a map going from no, let me write it like that. No, I'm going too fast. So first of all, okay. Let me start with the maximum of the degree equals to D. Well, so this I do not have FDDN. So this is the projective space associated to the polynomials of degree less than D at the power n plus 1 minus the projective space corresponding to the polynomials which have a degree which is less than D minus 1. So this is exactly the difference of projective space I wrote here. So this is P n plus 1 D plus 1 minus 1 minus P n plus 1 D minus 1. Okay, so I get the first one. And then the map which goes from, let's say, well, okay, so I wrote I D minus times the polynomials of degree less than I at the power n plus 1 into the polynomials of degree less than D power n plus 1, which sends simply some polynomials P times Q naught Qn onto PQ naught PQN. Okay, and if I start with polynomials here, which have GCD equals to 1, well, I'll get that the GCD is here is exactly equal to P. So this gives an embedding of the affine space of dimension D minus I times the scheme of the morphism of degree I from P1 to Pn into, well, in fact, it goes into Fd dn. And the Fd dn is exactly the disjoint union of the images of these maps. And I put Fi dn, which will be the union for j going from 0 to I of the image of this farm map. So A d minus j k times the morphism j from P1 to Pn. And of course, you see that if we want, well, in fact, we are interested in the first one, so in the morphism of degree d. So this is an open subset of FDDN, and we get, as was stated earlier, that morphism of degree d from P1 to Pn is an open subspace of this projective space. Is there any question about that? About the proof? Okay, so you may see that the proofs of the two results are very similar. I'm doing exactly the same thing. I have a GCD condition, I have to remove the GCD condition, I do it. So this is exactly the same from the point of view of the proof. However, the traduction of the result is not so obvious. When you look directly at the two propositions, well, it's not so clear that they say exactly the same thing. So I have to extend a little bit my dictionary to be able to do this translation. So let me start by rewriting the result for Pn of Q. So I won't make many changes, but I just want to write it in that way. So, proposition prime. Well, we have that the number of points of bounded height on the projective space for the height h divided by b at the power n plus 1 goes to some constant as b goes to infinity. And this constant, I may write it as 2 at the power n, well, multiplied by the product over all prime p, all primes p, of 1 minus 1 over p times the cardinal of the projective space over fp. Oh, I forgot, divided by p at the power n. So I simply wrote that 1 over zeta of n plus 1 is equal to the product over all p of 1 minus 1 over p to the power n plus 1. And I get this formula. So I hope tomorrow it will be clearer why I want to introduce this number here on this Euler product. Okay, so now I would like to do a similar thing for the geometric setting. Well, at once we see that there is one little problem. In the geometric setting, what is the meaning of the limit? We have some moduli space, and well, what does it mean to take the limit of the moduli space as d goes to infinity? So for that, I need a tool. once again, I'm using something which is quite well known, which was, I think, introduced by Kontsevich. So, which is, well, let's call it the ring of motivic integration. So to be more precise, well, so little k is a ground field. So any ground field. And, well, M of k. So as a group, I define it by generators and relations. So the generators so I take as a set of generators a set of isomorphism classes of varieties over little k. So and the relations are given by, well, let's say V is equal to U plus F if U is an open subset of V and F is equal to the complement of U in V. And in fact, one can extend the map, well, which sends a variety to its class in this ring to a scheme to the schemes of finite type. So to non-reduced schemes by taking more or less the class of V will be the class of the corresponding reduced scheme. So in that way, we can, it's possible to put a ring structure on MK so that the product of the class of X and the class of Y is equal to the class of X times Y. Okay, so up to now I have some ring, okay, but I'm still not able to do limits. So to do limits, I introduce a Tate symbol, which is a class of A1 in this ring, and then I define mklock to be the extension of mk in which I invert L. So if you prefer, this is mk of t over 1 minus lt. And then the spirit of the thing is that somehow one want to say that something with the dimension of which goes to minus infinity will be negligible, so tends to 0. So I define a filtration of this ring mklock, which is generated, so this is a subgroup generated by elements of the form so L minus I times V, where I minus the dimension of V is bigger than M. So somehow things with small dimension, small in Z. Okay, and then, well, this defines the topology, a metric topology on MK, lock. Well, a neighborhood of 0 in MK, such as the neighborhood of 0 in MK contains Fm of MK lock for some M. And I take then MK hat to be the completion of MK for this topology. MK log, sorry, for this topology. So the point is that in that MK hat, I'm able to take the limits of the class of moduli space. Okay, so now I have the tool I needed to be able to look at limits. Well, in the case of projective space, in fact, things turns out to work very well. And in fact, we don't even need the completion to have a limit. So anyway, so let me write a corollary of the previous result. So the corollary may be written as follows. So I look at the class of the morphism of degree D from P1 to Pn over little k. So this is the class of the scheme. And I divide it by L at the power D times n plus 1. And this converges to a constant as D goes to infinity. And this constant will be, so, L power, well, let me write it first like that, n plus 1 minus L times Ln minus 1 over L minus 1. And this converges in MK log. Well, okay, so how do I prove this corollary? Well, the proof is quite simple using the preceding proposition. Since if I look at the class of a projective space, then this is simply L n plus 1 minus 1 divided by L minus 1. So I should say that I did not invert L minus 1. But of course, this is a polynomial in L, so it makes sense. So therefore, we get the relation, the following relation. It will be L d plus 1 times n plus 1 minus L at the power d times n plus 1 divided by L minus 1 is equal to the sum for I going from 0 to D of the class of what we are interested in, morphism of D from P1 to Pn. Oops, sorry, morphism I from P1 to Pn times the affine space, that is L at the power D minus I. And from this, you get a formula for the morphism from P1 to Pn. So I'm not I may make a little mistake here, but I think one gets that this is L d minus 1 n plus 1 times, I think I forget something. Okay. I have to check the formula. Divided by L minus 1. But I have to check my formulas. I think I have a small mistake somewhere. So let me check it. Okay, this one is correct, but the previous one is not. So this one is not correct. I have, I think, to divide by L at the power n plus 1, something like that. Sorry. I wrote it slightly differently in my notes, so I have to reconstruct what I wanted to say. Well, there is some power of L which has to be corrected here. Yeah. Maybe something like that. Up to some power of L anyway. Well, I think it's, if I compare the two formulas, it should be n plus 1. Anyway, okay, so but here we have a nice aspect which will be useful for the next lecture. Namely, we have a product over all primes P of something which is related to the cardinal over Fp. So we would like to have a similar Euler product. Well, over a finite field, it will be okay. So over a finite field, over a finite field K, or let's say Fq, then I have a map which goes from Mk to Z, which simply sends the class of a variety V onto the cardinal of the set of points of V over Fq, and which sends, in particular, L over Q. So this, in fact, induces a map from Mk log into Z over 1 over Q, which is a morphism of rings. So this means that I can apply this morphism to these numbers, and I get a result So I get that, in fact, the cardinal of the morphism over Fq from P1 to Pn of degree D, well, divided by Q at the power D times n plus 1, converges as d goes to infinity to Q over n, 1 minus q minus 1 times, let me write it again, 1 minus q minus n, 1 minus q minus n minus 1. But there you recognize something you probably know, namely the zeta function of P1 over Q. So more generally, if V is a scheme of finite type over Z, you may consider the zeta function, well, zeta V of S, which is a product over all closed points X, so closed point of V of 1 over 1 minus the cardinal of the residue field of X at the power minus S. And in particular, for P1, what you get so zeta for P1 of S is given by 1 over 1 minus Q minus S times 1 minus Q minus 1 minus S plus 1. So it's not completely obvious, but you can prove that there is a simple formula like that. If you look here, well, you recognize that, in fact, the constant here may be written as Q over N over 1 minus Q minus 1, 1 over zeta P1 of N plus 1. As was the case for the number field Q. So I can again write this constant as Q power N 1 over 1 minus Q minus 1 for the product over all closed points of P1 of 1 minus 1 over the cardinal of the residue field times the cardinal of Pn over the residue field of P divided by the cardinal of the residue field at the power N. So once again, I can write it with a Euler product. So the formula is very similar to the one we had before. Well, I want to do the same in the general geometric case. But I run into troubles if I want to take a similar definition in the general geometric case, because I will have to do the following thing. So I would like to consider the product, well, for all points closed in, let's say, the projective line of, let's say, well, 1 over 1 minus L at the power, well, let's say S times the degree of the residue field over little k. Okay, this is formally what I want to have. Well, except that here I am taking a product, well, let's say if it is over C, I want to take the product, taking the product over C union infinity. So not it's infinite and it's not even countable. So I have to give some meaning to this infinite product. Well, that's not too hard. Because even over Q, you know that the formula, that zeta Q of S is equal to the sum. You might write it as a sum instead of writing it as a product. And similarly, in the finite field case, well, you can write zeta of, let's say, a curve for S, well, as a sum for D, so curve over FQ, some finite field of cardinal Q. So this is a sum for D bigger or equal to 0. And the sum for D divisor of degree D and C, well, times what? Times Q at the power minus D times S. Okay? So I can write it again as the sum for D bigger than 0, the cardinal of the divisors of degree D and C. So this is this symmetric product of the curve times Q at the power minus ds. And then, once I have done that, well, this I can translate in the general geometric setting. Because it makes sense to look at the symbol of Z at the power D. So finally, I can define, let's say, a motivic zeta function. So motivic. So let me write it correctly. So if I take C smooth projective curve over a field little k, then I define the motivic zeta function of C to be the sum for D bigger than 0 of the class of C, this symmetric product of the curve times T at the power D, which belongs to Mk, the formal series over Mk. And in fact, these functions were studied by Kapranov. So there is a theorem of Kapranov. Which more or less say that everything which can be hoped for this motivic height zeta function is true. Namely, this function for a curve may be written as P of t over 1 minus t times 1 minus lt, where P of t is a polynomial with coefficient in Mk. The degree of P is twice times the genus of the curve C. And moreover, it satisfies some kind of functional equation. So everything which we can be hoped for this function is true. And for P1, here you take that you get that P of t is equal to 1. Well, I should say at this point that some people have tried to generalize this not to a curve but to a general variety. But up to now it does not work so well, so it's not clear right now what should be the generalization of the motivic zeta function for a variety of dimension bigger than 1. But for curves it works very nicely. On taking this into account and the formula which I probably erased stupidly before, yes, I erased it. So the formula I obtained for the limit of the quotient, well, we get that corollary prime, which is that, well, if I take the morphism of degree d from P1 to Pn over little k, divided by L at the power n plus 1 times d, this converges as d goes to infinity in mk log to, in fact, so L at the power n over 1 minus L minus 1 times zeta, the zeta function of P1 motivic evaluated in L at the power n plus 1 sorry, it should be minus n minus 1, and which may be seen, well, formally as L at the power n over 1 minus L minus 1 times the product over all closed points of P1 of 1 minus L minus 1, well, times the symbol of, oh, sorry, I forgot, yeah, I have to take the degree into account, so the degree of P, Pn over the residue field at P, so which I may see, in fact, as a variety over little k. Divided by L at the power, the degree at P times n. Where d of P is equal to the degree of the residue field all over little k. So once again, this is a very big product, but by what I said earlier, this makes sense. So this concludes more or less the first description of the result for the projective space. So what I want to go into now is the question of distribution of points. So what do I mean? What do I mean by that? Well, the idea is the following one. Well, we can put it in a very general way. So imagine that we have some set S which is contained in some topological space T. And we have a function h which goes from S to R such that for any b in R, the set of little s belonging to capital S such that h of S is less than b is finite. Then we can consider the following measure. Well, let's say mu h less than b, which will be a probability measure, which is the sum for s such that h of s is less than b of the Dirac measure at s divided by the cardinal of the set of s in capital S such that the value of h in S is less than b. So this is a probability measure. Then to describe the distribution of S in T is simply to look at the limit of this measure as b goes to infinity in a weak sense. So in fact, well, is there a measure, let's say omega on t, such that for any continuous function f on t, one has that the integral of f with a measure as just defined mu h less than b over t goes to f omega over t as b goes to infinity. Okay, so that's exactly what we want to do with the rational points of the projective space. So for that I have to define, well, I have to embed Pn of q in some topological space, so we can do it in several ways. So okay, so this will be 2a distribution of Pn of q. So so let me start with well, the easiest case. So let me start by looking at Pn of q contained in Pn of R. So this is a topological space, which is a compact topological space. So the result is the following one. So define a measure on Pn of R in the following way. So it will be a Borelian measure. So for any open subset U in Pn of R, well, I should have written, so let me put a notation for pi will be mapped from Rn plus 1 minus 0 to Pn of R. Then omega of u will be the volume for the usual volume on Rn plus 1 of the x naught xn in pi minus 1 of u such that the maximum of the absolute values of the coordinates is less than 1. Yeah, and that maybe I should divide it by something, because this is not a probability measure. So let's say omega naught of u, and then omega of u is omega naught of u divided by omega naught of Pn of r, which is simply 1 over 2 at the power n plus 1 omega naught of u. Well, okay, now I can write the proposition. Well, for the height which I defined earlier, this measure, mu h less than b, on Pn of r converges to omega as b goes to infinity. So it's converges in law as I described just before. So I do not want to give too many details about that, but let me simply state, well, there is a first point, is that in fact it is enough to find the limit of the following quotient . So of quotient of the form, so the set of P in Pn of Q such that, well, the height of P is less than B, and, well, I have some, well, let me write P is equal to x naught xn, and I have some relations in like something like xi is less than lambda ig xj. I have to be, no, that's okay, for some lambda ij in R divided, okay, divided by npn h of b for some, so I just said lambda ig in R. So in fact, if you remember the picture I gave at the beginning, the idea is to look at some open subset of the projective space and look at the number of points which are in that particular open subset divided by the total number of points. Okay, and now, so you see the picture that we get. The picture we get is that we are looking to up to a GCD condition to the set of x naught xn in Z at the power n plus 1, such that, well, the maximum of the coordinate xi is less than b, and we have similar condition xi less than ij xj. I realize that there is some problem with the sign. I should choose something about the sign. It's not completely well written. Okay. Okay, I think it's, yeah, you can reduce to that. No. Otherwise, there was some problem if you change the sign of the coordinate. Anyway. You do this, and this is quite easily seen to be exactly what you expect. Namely, the volume, it's equivalent to the volume of the domain you are looking at. So, the cardinal of this set is equivalent to the volume of the corresponding domain. The maximum of the x size is less than b, and xi is less than ij xj. Well, if it's not empty. Okay, so once you have done that, you have proven more or less the result which I stated just before. So if you look at that, and if you remember very well the picture I have shown at the very beginning, then you will realize that in fact the picture I gave at the very beginning was not related to the maximum of the absolute values. Because in fact there was more points in the center than on the boundary. And this was used that, in fact, I was not using the maximum of the coordinates in the picture. So I have been cheating a little bit about the picture. What I've done in the picture is to use the square root of the sum of the squares of the coordinate. So in fact the picture I've shown you is with h prime, which is given by h prime of x naught xn is the square root of the sum of the square of the coordinates if x naught xn belongs to z at the power n plus 1, and the GCD of the xi is equal to 1. Well, and then the measure we get is not the one I described just before, but it's one which is not that different, namely the measure we get, as you can see from the proof, comes from the measure which is omega 0 prime of u will be the volume of the points in p minus 1 of u such that the square root of the sum of the coordinates is less than 1. Okay. So this corresponds to a ball instead of corresponding to a cube. And I think I should maybe stop there for today. So is there any question so far?